Okay, hi everyone. This is the second video of the 10th week when we will discuss approaches called block modeling and something called stochastic block models. So in the previous videos we have already discussed approaches for partitioning nodes in a network into some reasonable groups, in some characteristic groups of nodes. And we started with so-called community detection or community structure of networks, which is probably the most well-known or well-developed division into groups of a network. And we've seen a couple of algorithms for detecting, say, communities, overlapping communities, communities of links instead of nodes, and so on. We will now continue with this topic. First, starting with approaches called block modeling. And these approaches, as you will see, are able to detect, for instance, community structure in a network and also other types of group structures. In general, they should be able to detect any type of group structure in a network. And these approaches were actually developed in social networks literature, in social sciences. So these are basically the first approaches for grouping nodes of a real network into some reasonable clusters. And afterwards, we will talk about also block models that, although they have a similar name, in contrast to block modeling, which is basically an algorithm to partition the network, block models are actually models of networks with some group structure, but you can also use them to detect the particular group structure. As you will see, these approaches are not described in any of your course books. So if you want further details on that, I recommend that you look at this book that we published in the beginning of the year. I also contributed a chapter, and there are a lot of discussions here on block modeling, stochastic block models, and so on. So this is basically the most recent book in network science on partitioning, block modeling, clustering nodes, and so on. So now let us move to the slides. Okay. So, as I said in previous videos, we already introduced approaches called community detection approaches, or communities that detect community structure. We talked about approaches that can detect overlapping communities, or that approaches that can partition links in a network, links in networks into groups. We also mentioned that there is a great distinction between community detection and graph partitioning, whereas graph partitioning doesn't care what kind of groups you're getting. They do not necessarily have to be some densely connected groups of nodes, as long as you have to cut as little links as possible to partition the network into further groups. So, and in this video, we will discuss block modeling and stochastic block models. I believe that we already saw this figure, which kind of tries to explain why these approaches are called block modeling, because if you take an adjacency matrix of a network and you rearrange it, so you permute the nodes, so the nodes in the first group appear first, nodes in the second group appear second, and so on, you should get blocks on the diagonal and off diagonal that basically correspond to groups of nodes. So in block modeling, or as it was, this was introduced in social network sciences, it's basically a simple clustering of nodes based on some concept of similarity between pairs of nodes. And this concept of similarity is usually called equivalence. Why? Because this is basically the foundations of these approaches are in mathematics. So the similarity is defined to be some equivalent relation that basically gives you some equivalent classes that will actually correspond to group of nodes in a network. And the basic idea of equivalence is that you define the similarity between the nodes based on their common neighbors. So you take the neighborhood of first node and the neighborhood of the second node, take the intersection, and larger this intersection, more similar the nodes are. So similar nodes are those that share common neighbors. As we will later see, there are two basic definitions of equivalence. First is called structural equivalence, the second one is called regular equivalence, and there are also like generalized equivalence, relaxed equivalences, and so on, which you can read about in this book. So once we have defined the similarity of the nodes to be something proportional to the intersection of their neighborhood, then what do people in social sciences usually do is they simply use some, let's say, hierarchical clustering approach, for instance, Ward's method, to cluster the nodes based on this similarity. And at the end, you will get an entire dendrogram of clusters, and you cut that dendrogram at some desired resolution to get some desired number of clusters. So most of the approaches in social science are based on hierarchical clustering. Sometimes people also use some approach that when you start with some division of the network into groups, let's say random division, and then you move nodes from one group to another in order to increase some quality function. This is something that in computer science we would simply call like greedy local optimization. However, in social sciences they have a special name for this. They call that kind of approach relocation algorithm, because you relocate one node from one group to another. And at the bottom we can see a simple example of the JAVAX class dependency network, and the first figure is showing you the adjacency matrix of that network, where nodes are basically ordered in some random order and you cannot really see anything. But when you use that some block modeling approach, you can see that it repermutes the nodes so that you can see some, for instance, dense diagonal blocks which will correspond to communities, then some cases of two groups. Here is the first group and the second group. Here is the second one, where you have a lot of links between the groups and only few links within the groups, which will kind of correspond to something that would look like a bipartite structure, and so on. And here the colors corresponds to different packages of JAVAX, and you can see that based on the dependencies between the classes, we can, at least to some extent, infer the package structure. Okay, so this is basically all regarding the algorithmic part. Now, what we are interested in the following slides is how to define the similarity between the nodes, or how to define this node equivalence. The first and basic approach how to define equivalence in a network, which is just another term for similarity, is basically to say that similar nodes or equivalent nodes are those that share a lot of common neighbors, or they have exactly the same neighbors. As you can see in this conceptual picture at the bottom left, you have two nodes I and J, for which you could say that they are equivalent because they share a lot of common neighbors. These are the three neighbors on the top, but they also have some other neighbors. And this idea that I just explained is called structural equivalence, in contrast to regular equivalence that we will discuss on the next slide. So how to now define this measure of similarity between nodes I and J? The first and the basic approach would be to simply take the size of the intersection of the neighborhoods of nodes I and J, basically the number of common neighbors. And you can define your equivalence in that way and then run some hierarchical clustering approach. Here I'm also showing you how to write down this formula using the adjacency matrix, where you simply go through all possible nodes x and you check whether x is the neighbor of I and x is the neighbor of j. In this case, the elements of the adjacency matrix will be 1, and you basically count the number of common neighbors. Now, this simple measure is rarely used because it has a couple of problems. The first thing is that, for instance, that the similarity or equivalence of two nodes is 3, meaning that those two nodes share 3 common neighbors. The question is this a lot? Is this little? Is this expected? And so on. In order to answer that kind of question, what we want basically to do is normalize this measure in some appropriate way. The simplest approach could simply be to normalize this value by the number of nodes in the network, to divide it by the number of nodes in the network, which will give us a measure between 0 and 1 that is much easier to understand than just some absolute value like 3. If we want to be exact, the number of common neighbors can be at most n minus 2, but in large networks using n or n minus 2 wouldn't make much of a difference. So the problem is how to normalize this measure in some reasonable way. And one approach that we can take is simply to use so-called cosine similarity or cosine index between the neighborhoods of the nodes, which was first discussed by Salton. So let's call this Salton's equivalence. So if we move to the blackboard, we know that you can write down the and y as the magnitude of those vectors times the cosine of the angle between those two vectors that I'm here denoting with theta. And if we rearrange this formula, we can get the dot product at the top and the magnitudes of the vectors at the bottom. Now, how to now use this formula to define the similarity? We can take the row or column of the adjacency matrix that corresponds to, say, one node I and the other node j, and take the cosine of the angle between those two vectors. And these vectors basically just represent the neighborhoods of the nodes. So basically, you take the dot product of the neighborhood of the vectors corresponding to the neighborhoods of the nodes and divide it by the size of these neighborhoods. And this gives us the basic formula called cosine similarity. So in order to define the cosine of the angle between the vectors that corresponds to neighborhoods of nodes I and j, we can simply take their dot product divided and the dot product will be simply the size of the common neighbors as we had above, whereas at the bottom, notice that if we are dealing with a simple undirected network that is also unweighted, these elements of the adjacency matrix here can only be 0 or 1. So if we take the square of that, of 0 or 1, it will stay 0 or 1. So I can remove the squares here. So then I'm just basically taking the sum of the values in the neighborhood of node I, which is simply the degree of the node, obviously. So if we write down the final formula, what do we get? is that the equivalence can be defined as the size of the intersection of the neighborhood divided by the geometric mean of the degrees of nodes I and j. So again, we have normalized the value in some reasonable way. Notice that the value here will always be between 0 and 1 corresponding to nodes that have exactly the... however, the value cannot be negative, although in theory, cosines of course can be negative. However, notice here that we have only positive terms, so the value will surely be non. And you can think also about other possibilities how to normalize this number of common neighbors. So for instance, instead of taking the geometric mean, you can take the arithmetic mean, which maybe will be more reasonable in some scenarios. Or you can take the maximum degree of nodes I and j, or the minimum degree. And when we will discuss measures for link predictions and other measures of node similarity, you will see that you can normalize this size of the shared neighborhood in many different ways. For instance, also, there is no reason that why I should divide the number of common neighbors by some normalization. I could, for instance, also subtract some expected number of common neighbors that two nodes I and j would have if, for instance, the graph would be formed at random. And as it turns out, this will actually lead us to a simple Spearman correlation coefficient between the neighborhoods of node I and j, and you can get the exact derivation in the Newman's book. We talked about the second measure. Let us also introduce the third measure, which again is exactly the same as before. The only difference is that you normalize things in a different manner. And how things are normalized here is that you normalize the size of the intersection by the expected number of common neighbors in, say, configuration model graph, where you fix the degrees of the nodes, but otherwise the node connect between. Sorry for this. Otherwise, the nodes connect between each other at random. So remember, for instance, for the configuration model graph, we know that probability of a link between nodes I and j is simply the product of their degrees divided by 2n. Now, what we would like to do now is that we would like to compute what is the expected number of common neighbors when of nodes I and j when you fix the degrees of the node. So here is my node I that has some neighbors, and its degree is k sub I. And here is my node j that also has some neighbors, and its degree is k sub j. What would be the expected number of common neighbors of nodes I and j? So, firstly, assume that node I chooses its neighbors completely at random, as it happens in the configuration model graph. Then node j comes and look at one of its links. Node j will put that link to some random node, and the probability that it will select one of the nodes that are already neighbors of k sub or neighbors of I will simply be k sub I divided by n, when n is the number of nodes in a network. So now we have only reasoned about one of the links of node j. Since node j has k sub j links, the total number of common neighbors of nodes I and j will simply be the product of their degrees divided by the number of nodes. And this is exactly the formula that you can here see on the slide. And I believe the first paper that investigated this was in 2006, where the first author is Like, the last author is Newman, and for that I'm here calling it like structural equivalence. And for instance, looking at the book that I mentioned, there will also be other approaches mentioned for how to define equivalence. Okay, so the next thing that we also want to discuss is so-called regular equivalence. That it's a bit more complicated, but as you will see, it's relatively simple. And also, the approaches for structural equivalence are much better developed than approaches for regular equivalence. So structural equivalence is that similar nodes have the same neighbors, whereas the regular equivalence says that similar nodes are those that do not necessarily have to have the same neighbors, but these neighbors must also be equivalent. So, for instance, if we look at this conceptual figure here at the bottom, you would say that nodes I and j are regularly equivalent because they all have three neighbors that are also equivalent between themselves, here shown with different shades of nodes. And in that case, you can actually detect groups of nodes that are not even connected. For instance, notice here that I and j have no common neighbors, but they are said to be regularly equivalent because they connect to other neighbors that are equivalent between each other. So how to now define this measure of regular equivalence? The first approach that we will look at, and that we will call standard regular equivalence, is shown here in this left picture. And you would say that I and j are regularly equivalent, here shown with dashed line, if they have neighbors that are also equivalent between each other. So I have this neighbor here at the top, and j have this neighbor here at the top right, and I and j are equivalent because those their neighbors are also equivalent. So how to write down the formulas? Let me make this smaller. Okay. So we would say that I and j are equivalent if we go through all the neighbors of node I, here denoted with x, and all the neighbors of node j, here denoted by y, and we basically measure how similar or how regularly equivalent these two neighbors are, x and y. So we get this basic formula here, and here alpha at the beginning is some normalization constant. And similarly, you can write this formula using the adjacency matrix as shown here on the left side. Now, this basic formula actually has a couple of problems. Imagine that I would like to compute the similarity or to itself. So sigma sub ii here. And if you look at the formula, x will go through all the neighbors and y would also go through all the neighbors, and then we will measure how similar these neighbors are. So if node I has three neighbors that are not similar between each other, this formula here will give us a very low number, saying that I is not similar to itself. And this is kind of counterintuitive. Normally, we would like to define that each node is also similar to itself. Going on, this problem is actually more severe, because if we take two nodes I and j that share a lot of common neighbors, according to structural equivalence on the previous slide, these two nodes should be relatively similar to one another. However, our formula of regular equivalence will only give them large high similarity in the case when these shared neighbors are also similar between each other. So how to deal with these problems is what people usually do is that you introduce another term here on the right side, which is simply the Kronecker delta operator of indexes I and j, which will be 1 when I and j are the same and 0 otherwise. And this basically solves our problems that I have just mentioned, because by introducing this term, every node becomes similar to also to itself. Okay, so we are done. We are left with this our final formula, and it turns out that I can also write this formula in a matrix notation as shown here at the bottom. Here sigma now is the entire matrix of similarities between the nodes. A is the adjacency matrix, I is the identity matrix, and alpha is some scalar, some normalizing constant. So again, we have some recursive definition that we already had in the case of centrality measures and so on. And how to now compute this entire matrix sigma that will tell us similarities between all pairs of nodes is, for instance, we will start with some wrong value for sigma and some initial value for sigma, and then we will reiterate this formula to get better estimation of sigma. So if we start with sigma 0, that is simply an empty matrix of all zeros, and if I plug empty matrix into here, identity matrix. And then if I plug this into the formula, what I get is alpha times adjacency matrix squared plus I. And if I plug this into formula again, what I get is alpha squared times adjacency matrix to the power of 4 plus alpha times the adjacency matrix to the power of 2 plus identity and so on. And this will be the values that we will get with some iterative approach. And you can immediately see the pattern where you get different powers of the adjacency matrix, and the most important thing here to see is that we only get even powers of the adjacency matrix. And I would just like to remind you what powers of the adjacency matrix mean, something that you surely know from some algebra courses, discrete mathematics courses, graph theory courses, and so on. So if I take the matrix A to the power of R, for instance, and I take the element in the ith row and jth column, what am I actually getting is the number of paths of length R between the nodes I and J. This is something that you can also easily derive by yourself. And now if you look at the formula or the derivation in gray that we have written, we are only taking into account paths of even length. So if two nodes have a lot of paths between themselves, they will have high similarity, which is reasonable. The problem is that we are only taking the paths of even length, and there is no good argument why we should only take the paths of even length and not also take the paths of odd length. It's problematic. So how to deal with that is that we can define the regular equivalence in a slightly different way. That will at the beginning look like that we are defining a measure that is not symmetric, and we would like it to be symmetric. Similarity between I and j should be the same as similarity between j and y, or j and I. However, at the beginning it will look unsymmetric, but it turns out that it actually is. And how to define this corrected regular equivalence is shown in this picture at the bottom. Right. We would say that nodes I and j are regularly equivalent, shown by this dashed line, if node I has another neighbor, let's call it x, that is equivalent to node j. So we are saying two nodes are equivalent if the neighbors of one are equivalent with the second one, with the other one. So to write down now the formula is basically we go through all the neighbors of node I, which are here denoted by x, and we measure the similarity between x and j. Again, we normalize the things and add this Kronecker delta for the same reasons as the adjacency matrix. And at the bottom, you can again see the of this formula written in a matrix notation where all the variables are the same as before. So if we again start with this sigma similarity matrix to be an empty matrix, matrix of all zeros, on the first step we get identity matrix, on the second step we get alpha times a plus I, on the third step we get alpha squared times a squared plus alpha times a plus I, and see the pattern. And in contrast to before, we are now not only paths of even length, but we are taking into account paths of all possible length, and it seems reasonable that this is how we should do it. Also, this normalizing constant, it turns out that this has to be smaller than 1 divided by lambda, where lambda is an eigen value corresponding to the that corresponds to the leading eigenvector of the adjacency matrix A. So this alpha will be surely smaller than will be smaller than 1, and notice that since alpha is smaller than 1, we are here giving higher weight to, for instance, paths of length 1 than to paths of length 2, and this makes sense. So longer paths should count less. And basically this is the final formula that we wanted to derive. I'm calling here this Katz's regular equivalence because it turns out that if you go back to see the slides on node centrality, when we have defined the Katz centrality, this is basically a generalization of the Katz centrality to measure the similarity between the node and every other node in a network. So this is also where this result that alpha must be smaller than lambda to the power of -1 comes from, and the name comes from, and so on. If we move on finally to this historical development, the first approaches, as we already discussed, were developed for graph partitioning in electrical engineering and so on. Then block modeling, the approaches that we have just discussed, and concepts of structure and regular equivalence and so on, were mostly developed in the 70s by social network analysis or social scientists. And this is like, say, 30 years before modern community detection computer science developed their own approaches for detecting some reasonable groups in networks. And these block modeling are very powerful approaches, but I rarely use them in practice. In practice, I believe that the current belief in network science literature is that the most appropriate or approaches or the most proper approaches how to partition the nodes in a network into some number of groups is something called stochastic block modeling or stochastic block models, which is something basically completely different than classical social science block modeling. And this is what we will also discuss in the following slides. So how are we with space? Just a second. Since this here is a natural point to make a break, I will make a break here and continue after it. So see you in a minute.